Alright, since we're on a roll, I just thought I'd go ahead and make another video and introduce PubMed as part of how we use in finding our terminators. We saw that we had a non-standard one, but there are papers out there that can help you. So this is PubMed. So actually we can drop down databases and there should be PubMed right here. And I can just type in lacA terminator and we can search and we'll find the paper I'm looking for. And yeah, it's the first one here. So DNA sequence of the lactose operon, the lacA gene, and the transcriptional termination region. So this was way back in, what year was this? 1985. So this has been around a long time. People know it. This is when they actually found the lacA sequence, and they suggesting for me the interesting part of this is the origin is from a plasmid transposon or virus. In other words, lacA was not an original sequence that naturally evolved from something else. It looks like it was a piece of foreign DNA that was incorporated here and evolved into the A sequence is what the analysis, the evolutionary analysis did. We don't do a lot of that in here. That is a lot of people like trying to find the history of genes, etc., what they evolved from. I'm into that, but we don't have time in this class for that. But you can investigate, say, COVID, where it came from, stuff like that with bioinformatics. And there is a lot of interesting information that can be gained from analyzing the COVID sequence, and I won't go into that. You can ask me privately what I think, but you can do that analysis. Now, let's see. We're going to look at this paper, and it gives us, here we'll just go to the PDF. It'll take it a second. Here we go. And it's going to tell us the termination sequence. So for at the end of the lacA operon. So here they've done, and you've got this whole sequence for lacA operon, just like the one I downloaded. Like I said, this is useful. This is why this exists in the database for lacA operon, because a lot of people study it. And here is some interesting plots. So here methionine codons are marked by the lower horizontal line. So what they were doing is they were looking just for methionines as a measure of where the genes might be. And sure enough, methionines are relatively rare. So if you find codon AUG, they're rare or more likely where? Well, look where it peaks and where it declines. It increases inside the genes. Well, this one, lacA, it decreased, which I better read that again. I don't want to tell you wrong. But here is where they think the termination is, and for the lacA. So could be a couple of different shapes, and in a couple of different places. This is where they are estimating the possible structures, and then they go and find it specifically. And they also talk about the weak terminators, which we will talk about later. But this paper, here is the terminator, the UAA, all right, and then here are the possible places for this terminator. And here we have the U sequence at the end. So this is what? This would be our row independent. Let's go back. Which one has the U's at the end? Right here, that would be your row independent site that is GC rich. So if it's this one, this is the GC rich, and I see G's and C's nearby. Yes, G's and C's up here. So this is the GC rich row independent site. So this would be the one that you would use there. There are some others that are possible, all right, and they show you these, but each of these would be your answer. All right, and so notice that this is, it says 6, you only get 4, and it even has a C in between. Uh, but they're there and they're immediate. They're right after it. So it's U, C, U, 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 and then you've got this loop. It's an odd looking hairpin, and it's not very long. The stem part here at the bottom is not long. This would actually be a pretty hard one to find. This one would be easier and easier. The longer the stem, the easier it is to find. So this would actually also be a pretty hard one to find. You have a very short stem, so this is the part that's going to show up on dot plot. So in other words, when you use dot plot, what are you looking at? You're finding this piece that binds. That's what dot plot can find. And one with a short stem is going to be really hard to find. You're going to be dependent on following those U's, and here you only have 4. So this one also would be probably a hard one to find. It's just that it is there. But I just wanted to show you how to use PubMed and how to use the papers to your advantage. Now that doesn't mean that this actually is the one. There was a possible one right here, and then a little further down. This is quite a bit a ways down. This is like 900 base pair further down, or almost 1,000. That would be a waste of resources. I don't think the bacteria would waste that amount of resource, so I don't think it's going to use that one. I think it would use one of these two, a couple of hundred base pair after the stop codon. So, or let's see, 150, 6,000. This is just way too far down, but easy to find because of the long stem. I would, yeah, one of these two are the two that you would expect. It's not too far. Now, in a eukaryote, you could find it that far down, but in a prokaryote, yeah, this makes much more sense that it's either this one or this one. Not much in the way of U's. There's one here, 2 down here. This one looks like it's the right one. This might be the other type if it's GC. Look at this. Is it G rich C or C rich G poor? Hard to tell. That would probably be the deciding factor. But I would say this one is the correct one. Just wanted to show you that as a little side note on the A, and how you can use the literature to your advantage. Now, your operons are probably not as well researched as the lacA operon. In fact, none of them are as well researched as the lacA operon. So there's a ton of material out there. But for yours, I want you to give it a shot. Like I said, I'll grade it pretty easy on the terminator part. Just make logical reasons for you to think that say that there's a terminator there. In other words, what? You need to find, using dot plot, find something that looks like it's a hairpin, and I've kind of showed you what hairpins look like, and then look for some U's or not some U's, or for G plus C or C rich G poor. All right, use those rules there and try to find your terminator. And you know the regions it's going to come, especially in a bacteria. You normally, after the stop codon, you don't go too far. 200 bases maybe max after the terminator, before you get after the stop codon. You're not going to go 1,000 base pair like in a eukaryote. You're going to go here, 50, 100, never more than 200 if I ever seen it. In fact, I don't think I've ever seen 200 for the terminator after the stop codon. So you don't have to go too far. And 50, 20, this one, if it's this one, you didn't go very far at all. Here, maybe 20, not even that, 15. This is probably more typical. And so this is a good spot. It's got the U's, even though they're not 5 really, or 6. They are right after it. There is a U right here. And but this one's hard because the stem is so short. And that's what you're looking at with dot plot. You're looking at this piece. Okay. Just wanted to throw this one in as an extra video.